So after looking at the definitions of limits and learning a little bit about their behavior and sort of playing around with a few examples, in this video we're going to get a little bit more formal, although not altogether formal, but we will look at the rules or the laws for calculating limits of different functions. This video will still deal with this sort of informal kind of description and use of limits. Further on, we will get into the actual formal definition of limits, and then we will use the definition to prove some of these laws. But in this video, we're not there yet. We're just still talking about the description of these laws and how we can use them. So usually we'll be looking at one or two functions. We'll define those. So we'll start with two functions, f of x and g of x. Okay, so we have two functions, and let's assume that we have limits for these two functions as we take x to approach a. So we say that there are these limits exist. Okay, so this will be equal to limit 1, and this will be equal to limit 2. Let's start with our first law. The first law is the limit of a sum is the sum of the limits. So let's write that down. The limit of a sum is the sum of the limits. Okay, what does that mean? It means that if we're looking at the limit as x approaches a of the sum of f of x plus g of x, well, in that case, that is equal to the limit of f of x as x approaches a plus the limit of g of x as x approaches a, or it is equal to L1 plus L2. So this is pretty obvious, and all the first laws really will remind you perhaps of the laws for manipulating equations. So here again we're allowed to add two functions and look at their limit, and if the limits of the individual functions exist, so as we defined here they exist, then we can look at the sum of the function as the limit of the sum as the sum of the two limits. For example, if f of x equals x and if g of x equals x squared, then the limit as x goes to 2 of f of x plus g of x is equal to the limit of f of x plus the limit of g of x, each one of these as they go to a. And in this case, since these are continuous functions, we just have our a equals 2, right? So we have f of x equals 2, and g of x equals 2 squared, which is 4, so it is 6. So that's obviously a very simple example, but this shows you how you can work with this first law. So we can move on to our second law. The second law now is the law of differences, and it's very similar, obviously, to the law of the sum. The limit of a difference is equal to the difference of the limits. So again, we're assuming that the limits exist, right? That we have L1 and L2. And in that case, what we're saying is the limit as x goes to a of f of x minus g of x equals the limit of x goes to a of f of x minus the limit of g of x as we take x to a. So in our previous example where we were looking at f equals x and g equals x squared, if we take that same limit, the limit when x goes to 2 of f minus g, in this case now we can say our first limit is again 2, and we're going to take minus our second limit, which is 4, so that would be negative 2. So again, simple example for a pretty simple and intuitive rule. So what happens once we're done with the sum and the differences, that we usually move on to a product. So our first rule or law as it pertains to product is that we take a constant and we multiply a function by a constant. So say c is a constant and the limit of f of x as x goes to a is L1. So we can look at the limit of c times f of x as x goes to a, and in that case it's equal to c times the limit x goes to a of f of x, or c times L1. And this is a very obvious rule. If we have f of x equals x, and say c equals we'll say c equals 3, and we look at the limit when x goes to 2 of 3 times f of x, we're actually looking at the limit of 3x, which is just 6, or at the limit of x with a 3 before, right? In this case, we'll remove the c out like we do here, and again we get 3 times 2 equals 6. So this is a very, very obvious law. What other types of products can we have? Well, we can have products of two functions, right? So our fourth law is looking at the limit of f of x times g of x when x goes to a. And again, in this case, if the limits of f and of g exist, for x approaches a, it equals to the limit of f of x times the limit of g of x, each one as they approach a. So in this case, it would just be equal to L1 times L2. We can look again at our usual example, f equals x, g equals x squared. Let's look at the limit when x goes to 2 of f times g. It is just equal to the limit x goes to 2 of f of x times the limit when x goes to 2 of g of x, which is just equal to x, which is equal to 2, times x squared, which is equal to 2 squared. So we have the end 8. So again, a rather simple law which works sort of intuitively, similar again to what we do with equations. Our fifth law is probably the more complex of all the laws that we've discussed till now, and that is because we're going to be looking at a law that has to do with the quotients. So when we divide, we always have an additional complication where we want to be sure that we're not dividing by 0. So in this case, we say the limit of f of x divided by g of x, as x goes to a, will be equal to the limit of f of x divided by the limit of g of x, right? Both as we go to a, but we do have a condition here. And the condition is that this is correct only if the limit of g of x as we take x to approach a is not equal to 0. So as always, we're not allowed to divide by 0. Okay, so again, if we look at our usual example, if f of x equals x and g of x equals x squared, and we look at the limit as x goes to 2 of f divided by g, then we just have the limit of f divided by the limit of g, which is equal to x, which goes to a, and x squared, which goes to a squared. So we get a divided by a squared, which is just 1 divided by a. So again, and we've assumed that a is not equal to 0, and in this case, a is 2, right? So we have a half. So these are the most basic laws that we use in order to calculate the limits of functions, and these, you know, that in this way we can separate functions into different smaller, more easy to deal with parts. So if we have a very complicated function, but we can separate it into several other functions, f, g, and h, say, that are more simple, then we have an easier time evaluating the limits of these functions. Some of the main examples we actually turn into their own laws. For instance, we have the product law that we can use in order to arrive at the law for powers. So if we're looking at the limit, x goes to a, of f of x to some power n, so we take the function f, we raise it to the power n, and we want to know what the limit of that is as we approach a. So here what we can do is we can apply repetitively the product law. So we can be looking at limit of x goes to a of f of x times f of x times, and you know, n times f of x, and we can separate these out repeatedly, recursively, using the product law, and so we get just the limit of f of x as x goes to a to the power of n. And so this is what we call the power law for limits. We also have a very simple rule, which is worth defining clearly here, and that is the limit of a constant. So if we have the limit of a constant as x goes to a, that is just equal to the constant here as well. Our eighth law is also very simple, and that is the special case when we take the limit of x as x goes to a, and we always say that that equals a. So that is our eighth law, and obviously we don't even have to use an example here to explain that. We have a ninth law, which is the power law, that the limit when x goes to a of x to the power of n, which is just another case of the sixth law, is equal to a to the power n. So the sixth law, remember, is where we take the limit of x goes to a of f of x to a power of n. So here our f of x is just x. And so that's another obvious example. The next one is less obvious, and we will look at a proof of this when we go into the more formal definition of limits. But in this, now we're looking at the limits of a root of a function. So say the function x, limit as x goes to a. What we're going to say here is, again, similar to the power rule, is that it is just the nth root of the limit of x as x goes to a. So we're actually looking at the nth root of a. And that is something that will obviously need to be more carefully shown in the formal part, but also we have to make sure that we're being careful that if n is even, right, if n is 2 or 4 or 6, then a has to be 0 or positive. We have the same law for a function where we're looking at the limit as x goes to a of the nth root of f of x. And in this case, we will say that that equals the nth root of the limit when x goes to a of f of x. And here, if n is even, we have to make sure that f of x, that the limit of f of x as x goes to a, is greater than 0. One final sort of law in these laws for using limits and applying them to more complex functions is the direct substitution one. So we can call this rule number 12. If f is a polynomial, so it's a rational function. Reminder, rational function can be given by a polynomial or division by polynomials. So in that case, we can use something called direct substitution. What does that mean? It means that the limit when x goes to a of f of x equals f of a. So this is just for a polynomial or a rational function. Again, we're looking at functions like x to the power of n divided by 1 plus x to the power of m, and so on. So that is a rational function. A polynomial would be, say, x plus x to the power of n plus x to the power of 3, and plus a constant or something. So again, polynomials or rational functions, if they are continuous, if we don't put in all sorts of holes in the function, then we can use direct substitution, which is really the simplest way to find the limit at a point. So this video really ran through all these laws, and mostly because they're common sense laws, and if you need to go through them again, but basically anything that would be intuitive to do with these limits is usually possible as long as the limit exists and you're not dividing by 0 or taking a root, a square root or another even root of a negative number. So we'll go on to look at more complicated cases, but for now, we will end this video with these laws.